The world changed forever when we split the atom. Immediately, the promise of limitless energy fueled dreams of utopian cities, atomic cars, and space colonies. But the military had a simpler, more immediate demand: power anywhere, anytime. What if you could take a fully operational nuclear reactor, bolt it inside a ship, and sail it right into a remote harbor, bringing a city's worth of electricity to any corner of the globe? This was the ambition. This was the terrifying reality of the MH-1A Sturgis, the world's first and most likely last military-grade floating nuclear power plant. The project began as a bold answer to logistics problems: a mobile reactor housed within a converted World War II Liberty ship, the atomic core in a tin can. The engineers took a fragile, complex nuclear reactor, the kind housed deep within a concrete containment dome on land, and placed it inside an aging, corroding steel hull designed for cargo. This was a colossal engineering compromise, a permanent, high-risk nuclear facility floating on a temporary, vulnerable structure. A simple collision, an extreme storm, or even basic metal fatigue meant the reactor's containment vessel was constantly one hull breach away from a catastrophic meltdown. The $700 million liability. While the initial cost was in the hundreds of millions, the true financial nightmare was the inevitable decommissioning. They quickly realized that once the floating reactor was too radioactive or too corroded to operate, the cost of safely dismantling, cleaning, and disposing of the entire ship, now a massive floating waste container, would balloon into the hundreds of millions, effectively turning a power solution into a $700 million liability. The threat to the harbor. The Sturgis didn't fail because the reactor couldn't run. It failed because the world realized the chilling strategic flaw. Operating a floating nuclear plant meant placing a potential Chernobyl right next to a major population center or a military base. A core meltdown in a busy port would render the harbor, the surrounding city, and miles of coastline permanently uninhabitable. Stay with us as we descend into the archives, because the true reason they abandoned the dream of the floating reactor was a terrifying, unanswerable question about what happens when a massive steel hull finally succumbs to the one force the military can't defeat: saltwater corrosion. The foundation of the MH-1A Sturgis was born not of cutting-edge naval architecture, but of post-war surplus. The vessel chosen for this unprecedented transformation was the SS Charles H. Kugel, a standard, mass-produced Liberty ship from World War II. Liberty ships were designed to be cheap, fast to build, and disposable. They were the maritime equivalent of a wartime cargo truck. They were fundamentally not designed to host a complex, fragile, and high-risk nuclear power system. The engineering challenge was immense. The reactor, designed by Martin Marietta, was a pressurized water reactor, a standard, reliable design. But placing it inside the ship required extensive modification. A massive section of the hull was cut out and replaced with a custom-built containment dome that held the core and its supporting systems. This dome was the primary defense against radiation, but it sat perilously close to the thin, single-layer steel hull of the aging ship. The entire structure was a study in engineering contradiction. The reactor needed to be shielded, so massive amounts of lead and concrete ballast were poured into the hull. This added tremendous weight, making the already obsolete Liberty ship even slower and less stable in heavy seas. The ship's stability became a constant, terrifying concern. Furthermore, the environment of the reactor was unforgiving. Unlike a land-based plant, which sits on bedrock, the Sturgis was constantly moving, subject to the perpetual stress of ocean waves. This continuous, subtle vibration and flexing of the hull transferred directly to the reactor's piping and containment dome. Engineers had to design complex, flexible joints and shock absorbers to isolate the reactor from the ship's movement, an expensive, high-maintenance system that introduced more points of failure. The irony was absolute. They had created a permanent energy source inside a vessel built for obsolescence. The $700 million floating plant was a nuclear time bomb whose timer was set by the relentless, grinding fatigue of cheap steel and salt water. The most chilling aspect of the floating nuclear plant was its intended operational environment. a busy, often populated harbor. The Sturgis was designed to be towed or moored close to a shore facility, distributing power to a base or a city experiencing a blackout or disaster. This meant that the worst-case scenario was exponentially amplified. Imagine a catastrophic failure, a sudden loss of coolant, a severe internal pipe rupture, or, most terrifyingly, an external event like a collision with a freighter or a terrorist attack. In a land-based plant, the reactor sits inside a thick concrete containment dome on bedrock. In the Sturgis, the reactor was protected only by its internal shielding and a relatively thin steel hull, with only the open ocean separating it from total collapse. If the reactor lost containment and experienced a core meltdown, the result would be a localized, massive disaster far worse than any conventional explosion. The hot, radioactive materials would breach the hull, sinking the ship and initiating a massive, immediate contamination of the harbor, the shoreline, and the local marine ecosystem. The scale of the potential human catastrophe was immense. Unlike a land-based accident, where prevailing winds dictate fallout patterns, a harbor disaster involves contamination of the water supply, seafood, and the city's maritime infrastructure. A core meltdown in a major port like Charleston or New York would render the entire port functionally useless and trigger mass evacuation and long-term economic collapse. The simple, undeniable fact was that the Sturgis was a potential weapon of mass destruction aimed squarely at its own host city. Military strategists quickly realized the tactical liability. Protecting a nuclear plant in a busy harbor from attack or accident was a near-impossible task. The potential for a floating dirty bomb was too great a risk to bear, even in the fever pitch of the Cold War. The project was slowly moving from military innovation to public relations nightmare, forcing the Army to confront the unanswerable ethical question: how do you evacuate a city from a slow-motion nuclear disaster they can see anchored offshore? Operating the MH-1A Sturgis presented a unique and complex human resource nightmare, combining the occupational hazards of nuclear power with the inherent dangers of naval operations. The core crew were U.S. Army Corps of Engineers personnel, trained both as nuclear operators and as seamen. Their jobs were high stress, high risk, and often compromised by the very environment of the ship. The nuclear reactor demanded continuous maintenance, including refueling and inspections of the core components. This work exposed the crew to chronic, low-level ionizing radiation, a risk managed by strict rotation schedules and specialized shielding. But on a ship, radiation exposure was complicated by the constant movement and the necessity of working in confined, poorly ventilated spaces near the reactor compartment. The more insidious, constant threat was corrosion. The crew's secondary, ceaseless duty was the battle against salt water eating the steel hull. Rust was not just an aesthetic problem. It was a fundamental security flaw. A corroded section of the hull near the reactor area meant a potential breach of the primary containment zone. The crew had to spend countless hours inspecting, scraping, and repainting the hull, knowing that every single patch job was a temporary fix to a permanent problem. The combination of these two stresses, the invisible, creeping threat of radiation and the relentless, visible decay of the ship, created a high-anxiety operational environment. It was a vicious cycle. The older the ship got, the more corrosion increased, demanding more maintenance time, which increased the crew's radiation exposure. The Sturgis was, by its nature, a high turnover, a high-risk assignment that was difficult to staff and sustain safely. The massive cost was no longer just the fuel and maintenance. It was the cost of protecting and continuously rotating the highly trained, perpetually endangered personnel. This dual threat of radiation and rust cemented the fact that the Sturgis concept was fundamentally unsustainable, forcing the military to confront the one financial problem they could not simply bury at sea: the astronomical cost of saying goodbye. The final, fatal flaw of the floating nuclear power plant was not an accident at sea, but the predictable, unmanageable cost of its retirement. When engineers first conceived of the Sturgis, they focused on the cheap energy it would produce. They largely ignored the immense, inevitable cost of what they called decommissioning and disposal, D&D, that a nuclear reactor, once used, is permanently radioactive, particularly its pressure vessel and internal components. On land, a power plant is surrounded by massive infrastructure to aid in its decades-long D&D process. The Sturgis was a complex reactor contained within a ship that was itself nearing the end of its structural life. The cost of safely dismantling the Sturgis was staggering, and it was the primary reason the mass production of floating reactors was never built. The entire reactor section had to be meticulously removed in a specialized, highly controlled dry dock. Every piece of piping, every structural beam, and the reactor vessel itself had to be cut, packaged, shielded, and transported as high-level radioactive waste to an authorized disposal site, like the Hanford site in Washington. The cost estimates for the Sturgis D&D alone, in late 1970s money, quickly soared into the hundreds of millions, a sum that was nearly twice the cost of its original construction and a large multiple of the total energy it produced. The project was an economic disaster. It produced a finite amount of electricity in exchange for a virtually infinite disposal cost. The money saved by its cheap power was instantly wiped out by the single, final invoice for its safe burial. The concept of building dozens of these floating reactors was abandoned because the U.S. military realized it would be creating a network of $700 million floating waste liabilities that would perpetually drain the defense budget. The Army's floating power solution was mathematically proven to be a financial black hole. The final bizarre fate of the radioactive vessel itself is a story of a desperate, multi-year attempt to hide the evidence of this colossal blunder. The official narrative for the MH-1A Sturgis was disaster relief and powering remote military outposts. But the true, strategic reason for its existence lay in the shadows of the Cold War and the unforgiving jungles of Vietnam. The Sturgis was a direct response to a massive, immediate logistical failure of the war effort as the U.S. presence in Vietnam escalated in the mid-1960s. The need for stable, massive electrical power in newly established deep-water ports and coastal bases became critical. Running hundreds of diesel generators was expensive, noisy, and required a constant, vulnerable convoy of fuel tankers, a prime target for the Viet Cong. The Sturgis offered a promise of silent, limitless power delivered directly to the point of need, eliminating the fuel logistics tail. In 1967, the Sturgis was towed from its Maryland shipyard, sailed through the Panama Canal, and deployed to Gatun Lake in the Panama Canal Zone, where it operated for a short time to train its crew. Its eventual destination, however, was clearly intended to be Southeast Asia. The Sturgis was a strategic asset designed to power the war machine, providing energy for massive refrigeration units, communications arrays, and military hospitals, all independent of local, unreliable grids. But even before it could be deployed to the war zone, the strategic flaws were evident. Its slow speed and massive silhouette made it an easy target for enemy submarines or mine-laying, turning the floating power source into a guaranteed environmental weapon for the enemy. The risk of the enemy sinking the Sturgis and contaminating a crucial harbor or waterway outweighed the benefit of the power it produced. The military realized that deploying a floating reactor was effectively giving the enemy a massive, unexploded, strategically vital radioactive landmine to target. The vessel never saw combat, but the chilling logistical problems it was supposed to solve only deepened, proving that even a military-grade reactor could not overcome the simple vulnerability of its own steel hull. The Sturgis was a technological anomaly, representing a failed vision of nuclear power that civilian engineers quickly rejected. While the Sturgis was a military prototype, the broader concept of floating reactors was briefly considered by commercial entities, but the engineering community saw the inherent madness. Civilian reactors are designed for permanence and containment. They utilize multiple layers of thick concrete and steel containment structures designed to withstand earthquakes, aircraft strikes, and pressure buildup. The foundation is bedrock. The Sturgis, by contrast, had containment based on a floating, flexible platform subject to saltwater corrosion and unpredictable motion. The civilian industry quickly concluded that the regulatory, insurance, and long-term liability costs of a floating plant were unmanageable. No major utility company could afford to insure a massive nuclear liability floating in their local harbor, vulnerable to weather, shipping accidents, and corrosion. The very flexibility that made the Sturgis mobile also made it structurally weaker and more prone to radiation leakage over its long service life. Furthermore, the design severely limited maintenance options. Unlike land-based plants where components can be lifted and replaced using massive gantry cranes, maintenance on the Sturgis was constrained by the small spaces within the ship's hull. This made repairs exponentially more difficult, time-consuming, and hazardous for the personnel. The fragility of its containment, the mobility that undermined its stability, and the high-risk maintenance environment meant that the concept of mass-producing floating power plants, whether for military or civilian use, was never built again. The Sturgis was a billion-dollar lesson. Putting a nuclear core in a boat is fundamentally unsound. The next stage of its failure, however, was a predictable yet terrifying consequence of its constant operation: radioactive accumulation. That a critical problem emerged within the Sturgis after just a few years of operation: radioactive accumulation in the containment vessel and the supporting systems. While the reactor core itself was designed to be eventually removed, the primary cooling loops, the shielding concrete, and the internal steel structure of the containment hull became permanently contaminated over time. This contamination meant that the Sturgis transformed, piece by piece, into a massive, mobile radioactive waste package. Every pipe rupture, every cooling leak, every maintenance procedure spread low-level radioactive isotopes within the ship's internal structure. This phenomenon had two catastrophic consequences. First, it drove up the maintenance costs exponentially. Technicians could no longer simply enter the reactor compartment. Work required remote tooling, temporary shielding, and limited dose windows for personnel, drastically increasing the time and complexity of even simple repairs. Second, it made the vessel an international liability. Once deployed, the Sturgis was effectively an exclusion zone on water. When the ship eventually had to be moved, its hull and internal systems had to be rigorously decontaminated and monitored to ensure they were not leaking radioactive wastewater or spreading contamination at sea. This massive floating waste risk was simply too great to ignore, forcing the military to severely limit its deployment and operation. The Sturgis spent its brief operational life effectively isolating itself with its own accumulating poison. It became a floating pariah, too dangerous and too expensive to move, too valuable to simply abandon, and too complicated to repair. The massive cost of managing its own self-contamination sealed its fate. The Army had no choice but to permanently immobilize the vessel, leading to its final, bizarre, and politically charged resting place before its ultimate burial. The MH-1A Sturgis completed its primary service not in the jungles of Vietnam, but in the tropics of the Panama Canal Zone. From 1968 to 1975, the vessel was towed to various locations in the Canal Zone, providing power to the U.S. military bases there. This 7-year deployment was technically successful. It generated stable power, but perfectly illustrated the project's strategic and logistical failure. The Sturgis was a solution looking for a permanent problem. It was constantly moving, yet never truly mobile. It was deployed to Panama because its perceived risks made deployment to a hot combat zone like Vietnam impossible. Panama became its semi-permanent parking lot, a place where it could generate power from military bases that, arguably, could have been powered more safely and cheaply by conventional means. The irony of its Panama service was the reverse vulnerability. The Sturgis was supposed to eliminate the risk of fuel convoys being attacked. Instead, it became a massive, stationary nuclear liability that the entire Panama Canal Zone had to protect. Any local political unrest or perceived threat to the reactor could have triggered an international crisis. The U.S. was essentially forced to deploy immense resources to protect the reactor that was supposed to be simplifying their logistics. In 1975, the Sturgis was finally deactivated. The reactor was shut down, and the nuclear fuel was meticulously removed from the core and shipped back to the U.S. But the ship itself, now a massive, heavily contaminated, floating hunk of steel, was too dangerous and too difficult to tow back to the mainland for immediate decommissioning. It was simply parked in the canal zone, awaiting its fate, a massive $700 million monument to a strategic failure, too radioactive to scrap locally. The vessel was stuck in a bureaucratic and radioactive limbo, leading to a massive, costly operation to safely transport the ghost ship thousands of miles to its final resting place. The decommissioning of the WWII Sturgis stands as a monumental cautionary tale in nuclear engineering. Once permanently shut down and defueled in 1975, the ghost ship had to be transported from Panama back to the United States for D&D. This was a complex, multi-million-dollar operation involving specialized teams and heavily monitored international transit. The ghost ship tow was a spectacle of military logistics. The Sturgis, now dead and highly radioactive, was slowly towed through the Panama Canal and across thousands of miles of ocean to the Galveston, Texas shipyards. The tow itself had to be conducted with extreme caution, as the aging hull, stressed by years of floating and motion, remained the primary containment barrier for the accumulated radioactive contamination. The fear of a hull breach and subsequent sinking at sea was a constant, terrifying risk. Once in Galveston, the massive, multi-year D&D process began. The Army's goal was simple: reduce the ship to its smallest possible component parts, removing all radioactive material for safe disposal. The most contaminated section, the entire reactor containment vessel and its surrounding compartments, could not be simply scrapped. This massive, two-story structure, weighing thousands of tons, had to be carefully cut out of the hull, packaged in specialized, thick-walled containment barges, and towed again. The final, bizarre resting place for the Sturgis's radioactive core components was the Hanford site in Washington State, one of the most remote and secure nuclear waste facilities in the U.S. The $700 million price tag was finalized, representing the cost of dismantling, towing, packaging, and permanently burying the radioactive shell of the failed reactor. The Sturgis proved that the cost of generating electricity was trivial compared to the cost of safely burying the waste. The concept of mass-producing floating reactors was killed by this final, crippling invoice, but the idea of mobile nuclear power found a parallel, equally risky military application that continues to define naval power today. The story of the WWII Sturgis is not just one of failure. It is one of selective success. The technology of a nuclear reactor floating inside a steel hull was proven, but only in a highly controlled, specific military environment: the submarine. The very reason the U.S. Navy rejected the floating power plant concept was because they had already perfected the ultimate application of the mobile reactor. The USS Nautilus, the world's first nuclear submarine, was launched in 1954, decades before the Sturgis. Naval reactors are compact, heavily shielded, and designed to operate under immense pressure, providing virtually unlimited endurance for vessels that could carry devastating power. The Navy accepted the risk because the strategic gain was absolute. Submarines could hide, strike, and remain undetected for months. The Sturgis, however, took the nuclear risk of a submarine, but stripped away the strategic advantage of mobility and stealth. It was a massive reactor, but it was unshielded by miles of ocean and limited to shallow ports. The engineers realized that the containment standards for a land-based reactor, or even a deep-diving submarine, were not applicable to a shallow draft, surface-vulnerable ship. The constant flexing of the hull, the perpetual threat of corrosion, and the need for frequent access for maintenance made the Sturgis fundamentally incompatible with the safety protocols required for nuclear power. The Navy understood that a floating nuclear plant was a strategic regression. Why risk contaminating a crucial port with a stationary reactor when a nuclear submarine could quietly move to a remote area, generating power from its engines, if absolutely necessary, and then submerge and disappear? The success of the nuclear submarine program highlighted the Sturgis's fatal flaw: mobility without stealth is vulnerability. The Navy had perfected the atomic ship that ran away from danger. The Army had built one that had to be moored in it. This stark comparison between the mobile fortress submarine and the stationary target, Sturgis, cemented the fact that the Army's floating reactor was a relic of poor strategic vision. The most enduring, practical legacy of WWII Sturgis is the catastrophic financial lesson learned from its decommissioning. The project's ultimate cost breakdown became a crucial, cautionary case study for every subsequent nuclear project globally. The engineers proved that the life cycle cost of a fragile, contaminated asset floating on water is orders of magnitude higher than its land-based equivalent. The D&D process involved not just cutting up a reactor, but the specialized handling of a radioactive ship hull. The entire hull had to be treated as contaminated waste, multiplying the final cost. The final budget confirmed the failure of the initial economic premise. The cheap power generated by the Sturgis was completely nullified by the astronomical cost of its burial. This singular event forced regulatory bodies and defense planners to adopt more rigorous standards for pre-funding decommissioning costs for all new nuclear projects. No government agency could afford to repeat the Sturgis's mistake of generating a massive, unfunded liability. The failure to build more floating nuclear power plants was therefore a triumph of fiscal conservatism and strategic planning. The world decided that no matter the energy crisis, the financial and environmental risk of creating dozens of floating radioactive hulls was an unacceptable burden on future generations. The Sturgis became the definitive symbol of too cheap to meter becoming too expensive to bury. The massive hull, once purged of its radioactive heart, still had one final, ignominious chapter to play out before its complete removal from the historical record, a testament to the Army's need to scrub the evidence of its failure. Once the core reactor and all highly contaminated sections were removed at the Galveston shipyard and shipped to Hanford, the hulk of the former SS, Charles H. Kugel was just a highly monitored, massive steel shell. It was no longer a nuclear liability, but an obsolete, decaying Liberty ship hull. The sheer size of the hull meant it could not be cheaply scrapped. After its decontamination phase, the ship, which began its life carrying cargo in World War II and briefly hosted the atomic age, was towed one final time. It was moved to the port of Brownsville, Texas, a major scrapping and recycling center. Here, the former MH-1A Sturgis was met with the final, brutal reality of its existence. The massive steel structure, once designed to carry the world's most advanced power source, was cut into smaller, recyclable sections by conventional industrial plasma cutters. Every piece of steel, the very structure that housed the nuclear reactor, was melted down, repurposed, and sold for scrap. The only thing left was the memory and the colossal financial accounting of its operational life. This final, ignominious journey, from a technological marvel to scrap metal, underscored the tragic obsolescence of the entire concept. The Sturgis was built to last forever with nuclear fuel, yet its supporting structure, the fragile steel of 1940s freighter, dictated its short, doomed lifespan. The Army had to literally erase the physical evidence of the floating Chernobyl from the world's oceans, concluding a decades-long effort to contain the fallout of a strategic mistake. But the ultimate, terrifying consequence of the floating reactor concept was its potential to destabilize the very laws of the sea, threatening the freedom of navigation for all nations. Beyond the engineering and financial costs, the widespread deployment of floating nuclear power plants presented an insurmountable geopolitical and legal challenge that ultimately killed the concept for good. This was a direct threat to the law of the sea. Imagine a scenario where dozens of nations deployed their own versions of the Sturgis. A nuclear-powered vessel, even one generating civilian power, would be viewed under international law with deep suspicion. Its presence in international waters, or even anchored near a neighbor's coast, would be seen as a direct infringement on national security and environmental sovereignty. The biggest threat was the right of innocent passage. Warships and nuclear power vessels are typically subject to strict international monitoring. The Sturgis, as a military-owned nuclear vessel, could be seen as violating the safety and environmental protocols of any nation it passed near. A terrorist threat to one of these floating reactors in international transit could force a dozen nations to scramble their navies and close their ports, creating chaos in global shipping lanes. Furthermore, who would be responsible for the cleanup in the event of a catastrophic failure outside of a nation's territorial waters? No single country wanted to accept the infinite liability of a floating nuclear-time bomb sinking in international shipping lanes. The U.S. realized that by pioneering this technology, they were opening a Pandora's box of international regulations and potential conflicts. The Sturgis was not just a naval asset. It was a diplomatic liability that threatened the fragile balance of maritime law. The global community collectively rejected the idea of dozens of potential floating Chernobyls, concluding that the immense strategic risk to maritime order outweighed the localized power benefit. The final chapter of this failure is rooted in the strategic decision to adopt a safer, equally mobile energy solution. The failure of the MH-1A Sturgis project was a victory for economic sense, environmental sanity, and international law. The military learned that mobile power did not need to be nuclear power. Following the Sturgis's retirement, the Army focused on rapidly deployable, high-output gas turbine generators and advanced diesel-electric systems. Power solutions that, while requiring fuel convoys, carried zero risk of a $700 million nuclear catastrophe and zero threat of contaminating a major port. The Sturgis remains a perfect example of Cold War technological excess. It solved a problem, energy logistics, by creating a far greater, unmanageable problem, nuclear liability. It taught the world that containing a nuclear reactor in a vulnerable, floating hull is fundamentally incompatible with long-term safety and financial solvency. The world wisely chose to bury the concept. The hulk of the Sturgis was recycled, its radioactive components entombed, and the financial lessons absorbed. Today, the concept of floating nuclear power is slowly being revived, but with hypermodern, passively safe, and highly robust reactor designs that attempt to address the failures of the vulnerable Sturgis. The $700 million floating Chernobyl was a machine designed to solve logistics, but it was defeated by the simple, unstoppable realities of salt, physics, and money. The Sturgis was a nuclear reactor in a ship, which proved too risky. Now, Russia and China are developing new floating nuclear power plants for commercial use. Considering the massive D and D costs and the risk of accidents at sea, do you believe floating nuclear power plants are an inevitable necessity for our energy future, or are they a ticking time bomb waiting to sink the global shipping lanes and cost billions in cleanup? Join the debate below and tell us whether the world was right to bury the Sturgis.